Hello and welcome to Lecture 4 of the Momentum Unit in Phys 1104, and finally we get to meet momentum itself. 2 lectures ago, after discarding several hypotheses, we found this one that was in agreement with a variety of experiments. And so I am now going to say that this one is well enough validated, and I'll say not just by me, that I'm not going to call it my third conjecture anymore. I'm just going to call it a law of Cart collisions. And now I want to see what I can do with it. And so I'm going to start manipulating it algebraically, right? I'm sure you do this all the time when you want to have a good time. You just take an equation and start manipulating it, right? So the first thing I'm going to do is I can see that I can get rid of my denominators. So I'm going to multiply both sides by MA, and I'm going to multiply both sides by delta VBX. And that's going to get rid of my denominators. So cancellation happens, and I wind up with this. And the thing to notice is that now everything to do with cart A is collected on one side, and everything to do with cart B is collected on the other side. The next thing I'm going to do is I'm going to say, well, my deltas have to be final minus initials. So I can replace them with final minus initial. And so I'm going to do that, and I'm going to do it this way, where I've already multiplied through by the m's. And you might follow along doing the algebra yourself, pausing every now and then. So the remaining step that I'm now going to do is that I'm going to collect all of my finals on one side and all of my initials on the other. So since this final is sitting here positive, and I'd like not to have negatives lying around if I don't have to, I'm going to collect my finals on the left and my initials on the right. So in other words, I'm taking this term over to here, and I'm taking this term over to here. Okay, so what? Well, what this is showing is that I have some quantity that I can build out of inertias times velocity components, and the total of that quantity appears to have been the same before and after. So if I define a P to be, and I'll say this is a px, and it is an m, an inertia, times an x component of a v. Then what I've got here, writing it this way, is I've got the final value of pa, x, plus the final value of p f of PB, equaling the same thing, but with, and I'll just switch the A's and the B's so I have the same structure on both sides. So this algebra was to give us several forms of this equation where we can see certain properties of this new quantity we've found, P. And this, finally, P, is momentum. So specifically, these p's I'm writing here are x components of momentum, which suggests to you that momentum must be a vector. And we'll see that more explicitly in a little while. So the plan for the next part of the lecture is to take these different forms I've written and see what they tell us about momentum. And we're going to see that momentum is a rather convenient quantity. It's always good to be aware of units, and notice that since this is an inertia times a velocity, it will have units of kilogram meters per second. I suggested that the momentum is a vector, but I should probably justify it. So let's look at one of the forms of that equation that we had as I was manipulating it. And let's think about what happens if we, as we can certainly do, just multiply both sides by I hat. Well, that means we are constructing, in this case, where the velocity is entirely along the x-axis, we're just constructing the delta v vectors instead of the x components. And so I'll put them onto the diagram like so, where this is the case I've drawn, where the double cart is initially at rest, but I didn't have to draw it that way. So now let's take this equation that I've got and draw what it means. And so I'm going to start by constructing these delta v's. There's delta VA, right? I've taken the final VA and I've subtracted the initial VA from it. And similarly, there's my delta VB. Since VBI is 0, I don't even need to use it in constructing that change. Now remember that what's going on here, in the case I've shown in the pictures, is that the MB is twice what MA is. And so when I now multiply those delta V's by the M's, I wind up with these momentum vectors, I'm claiming, where it becomes clear if you look at the picture that PA is equal to negative, or delta PA is equal to negative delta PB. Okay, but so far all I've really done is multiply through by I hat and then rename some things. But let's now think about what happens when you rotate the axes. So I'm going to superimpose those axes on these two P vectors and show what the components look like. And lo and behold, look, you can see that the x components of the delta p's obey that delta PAX is negative delta PBX, and the y components are doing the same thing. And so the original form of the equation that we had, which we just wrote for one component, has held for both components now that we've rotated the axes. And so this is showing that this is a vector relationship. It holds independently for the x and y components. And I'm going to say that this is unsurprising because we built a law here out of inertia, and inertia doesn't depend on our choice of axes, and we built it out of velocity, and we also know that velocity doesn't depend on our choice of axes. And so this law, which is saying that the changes in the momentum of these two objects are equal except for a negative sign, is independent of our choice of axes. And this is part of its vector nature. Now let's think about different system definitions and see what it tells us. So we know, now that we can write P as a vector, that we can write our law for the cart collision this way, that the initial sum of the p's equals the final sum of the p's. So think of what that means. We can think of our system as the pair of carts, and we then have a total momentum of the system, which is apparently just a sum of the momentum of the one cart and the other cart. So this is just like if we think of dividing the system into two halves, might as well call them A and B. Well, our total momentum is the sum of the contributions due to the two parts. And this is exactly the sort of behavior we expect for an extensive quantity. Well, this is great because we've seen that extensive quantities have this very convenient set of accounting principles that we can apply to them. And so it's very useful to discover when a physical quantity is extensive. There's another way to see that momentum is extensive. If you think of a single or standard cart moving along at some velocity v, and then you think of a double cart also moving at the same velocity v. And so let's consider each of these to be a system. And the inertia of the double cart is clearly twice the inertia of the single cart. So the momentum of the single cart is just its inertia times v. The inertia of the double cart, or the momentum of the double cart, is just its inertia times v, and that is exactly twice the momentum of the single cart. So what we see is that if we keep the v's the same, so keep everything the same except double the system size, the momentum doubles. And so the momentum is proportional to the extent, the size, of the system, and therefore it's an extensive quantity. To get an intuitive idea for the meaning of momentum, let's compare some similar situations. So here we have two objects, let's say they're cars, and they're moving at the same speed, but one has twice the inertia of the other. And here's a vague question. Which of these two situations has more motion? Well, despite how vague the question is, I think you would agree that this one has more motion. In fact, perhaps you would agree that it has twice as much motion. And indeed, notice that it has twice as much momentum. Well, here's a different situation. Now the cars have the same inertia, but one is going twice as fast as the other. And again, if you ask which has more motion, I think you would agree that this one does. And again, it's reasonable to say that that's twice as much motion. The matter that is moving twice as fast. And it has twice as much momentum. So we can think of momentum as a measure of the amount of motion in our system. Inertia and momentum aren't particularly commonly used words in everyday speech, but when people do use them, they tend to use them to mean almost the same thing. And this leads to some confusion because in fact they're very different. For example, inertia is a scalar, but momentum is a vector. Inertia is an inherent property of an object. You can't change an object's inertia except possibly by breaking it up into pieces, but then arguably you've got a new, different object. Whereas momentum can be changed easily. You just have to change the object's velocity. Inertia is the amount of matter, but momentum is amount of motion. And inertia is a resistance to change in velocity, but momentum has nothing to do with that. They do have one thing in common, though. They're both extensive quantities. Remember that interactions cause objects to accelerate. In fact, that's practically our working definition of what an interaction is. Well, acceleration is the rate of change of velocity, so interactions cause objects' velocities to change. But of course, momentum is calculated from the velocity, and so the other thing that's clear is that interactions change the momentums of objects. As an example, at one extreme is an air puck. It moves along at virtually constant velocity, and that's because it has virtually no interactions with the things around it. And so its px versus t graph is just going to be another straight horizontal line because all you're doing is multiplying vx by the air puck's inertia. It's just a rescaling of the graph. So now let's think about the book sliding along the floor. It rapidly accelerates to rest, and that's because it's interacting strongly with the floor as long as it's moving. And so its px versus t graph is also going to show a rapid change in the momentum. Let's apply that reasoning to a cart collision. So here's a typical vx versus t graph, and we can see where the carts are interacting with each other because their velocities change. Well, when you multiply by the inertias, all you get is a graph that looks like this, where what we know is that the changes of the momentums of those two carts are equal in magnitude but opposite in sign. Now let's think about, instead of the carts individually, think about the green box surrounding the system containing the two carts. Well, what our momentum equation is telling us is that the change in the momentum of this whole system is zero, or equivalently that the initial and final momentums of the system are the same. And so on the graph, the system total momentum is just a constant. And that makes sense because even though each individual cart is changing its momentum because of the interactions between the carts, the system is only interacting very weakly with the environment, and so its momentum is remaining roughly constant.